Well, hello, this is the lecture on orbital dynamics. And so this is where we'll be talking about the inverse square law. And the inverse square laws are critical, for instance, for gravitation. And so a lot of what we'll be talking about in this topic is orbital motion around gravitating bodies. These are going to be central forces. And so a central force is a force that depends only on the relative distance between two masses. And so that's clearly going to be the case for gravitation. So we'll cover a couple of principles in orbital dynamics. One is going to be conservation principles. We'll see that we have conservation of energy. We'll also have conservation of orbital angular momentum. And then we'll talk a little bit about conic sections, because the solutions to the equations of motion will be ellipses or parabolas or hyperbolas. And one of the really key concepts of this topic is something known as an effective potential. And so an effective potential is a way of including angular momentum effects, but in a one-dimensional dynamic just on the radius coordinate. All right, so let's consider the case of two bodies. So the two-body problem is exactly solvable, and whereas the three-body problem is actually not solvable. The three-body problem will exhibit chaos, and there is no analytic solution to the three-body problem. Two-body problem is exactly solvable, and so we'll spend the next half hour to 45 minutes talking through how we're going to solve for the equations of motion for the two-body problem with the central force, and we'll see that the solutions will be these conic sections. All right, so let's talk about the two-body problem. So let's say we have a mass m1 and we have another mass m2, and there is a force exerted by by each on the other. And so, for instance, here's the force of 2 on 1, and here's the force on, let's see, the force by 2 on 1. This is going to be the force on 2 by 1. And the forces are equal and opposite. You can see them along the line connecting. But let's say that we have the origin down here somewhere. And so we've got our origin off somewhere that we've maybe decided to set it there for convenience, although obviously this is a bad choice. We want a better choice, all right? The better choice is going to be center of mass. And so somewhere between these two is going to be a center of mass, and the masses, these m1 and m2 aren't equal masses, and so we'll have to find out where that is. And let's say then that I want to have a position vector r from the origin to the center of mass. So what I'll want to do is actually define this position vector r, and so I'm going to define it down here. And so the r is going to be 1 over the total mass, and then the sum over the masses and the position vectors. And to make our lives really easy, what I'm going to do is, once I've found that quantity, I'm going to set my position vector r so that it is at that center of mass. And so then we'll be describing all the dynamics relative to the center of mass origin. And so for the case of two bodies, this sum is really simple. It's just m1 times r1 plus m2 times r2 is equal to 0. We are going to define a relative coordinate r, and so here I have r as the relative coordinate between 1 and 2. You can pick either r1 minus r2 or r2 minus r1. It doesn't really matter. In a case like the solar system, obviously, what we'll be doing is having the sun be the relative position, and so the sun would be, in this case, the r2. And so it would have r1 minus r2. Mostly relative to the sun, although we'll see that there is going to be a center of mass which is not at the center of the sun. It's going to be shifted a little bit off of the center of the sun. And so what we do is we solve this equation with this definition of the relative coordinate r, and what we get is are these two equations down here in the box. And so that's the equation for r1 relative to r, and then this is r2 relative to r. One is minus the other because they're oppositely oriented. And so I can take this solution for r1 and r2 in terms of r and plug that into the Lagrangian. And so the Lagrangian is just working with the original coordinates of r1 and r2. I have a 1/2 m1 r1 dot squared, or 1/2 in front, and then a 1/2 m2 r2 dot squared. These are the two kinetic energy terms. And then I've just got this potential energy, which is the potential energy of the central force between the two particles. So let's go ahead and plug in for R1. That gives us this term here. Plug in for R2, it gives us this term here. And then those actually combine into this new term. And you'll notice that what I've got here is just this relative coordinate r, and then it's dotted, so that's the speed squared. And then there's this item or this coefficient in front, which has units of mass, and that's called the reduced mass. And so the reduced mass is an important idea. It's this idea that we can reduce the dimensionality of this problem. That basically the two-body problem becomes a one-body problem, and it's in terms of this relative coordinate r, except that the mass that shows up is not mass 1 or mass 2 alone, but it's actually a combination of the two. And one way to also think in terms of this reduced mass is that 1 over the reduced mass is equal to 1 over m1 plus 1 over m2. And so this is kind of like adding capacitors in series. It's totally different physics. It's just mathematically the same. And so the reduced mass is really what you're doing is you're adding the inverses of the masses. And so this is giving you the reduced mass for a one-dimensional problem in which we have just a single relative coordinate. All right, so now what we've done is reduce the two-body problem to a one-body problem. And so what we'll have is a center of mass. And so we'll have a center of mass, and we'll have a effective mass mu, which is undergoing through a central force, undergoing some kind of an orbit. And so what we'll see is that we've got two coordinates. So it's a one-body problem, but it's going to be in the plane. And so we'll have coordinates. And so for instance, we'll have position vectors, and that's this r is actually the relative position vector between the two masses, but now we actually stop thinking about that. We just think of this as the position from the center of mass to the location of a reduced mass or an effective mass or reduced mass of the problem. We'll also have angles, and so we'll have choices we can make. If this is an ellipse, we can define angles as the angle swept out, let's say from the position of closest approach or the position of farthest approach. In this case, let's actually take the position of closest approach. Now in terms of our angles, this would normally be, I'm going to say phi, because it's the azimuthal angle of the problem, and then that would set our plane to be theta equal pi over 2. What I'll be doing though is just because most of my notes are actually written in terms of theta, let's just actually, since we know that this is in the plane, let's just go ahead and call the planar angle for these dynamics theta. All right, so when I'm talking about theta, I'm actually talking about the angle in the plane. All right, so what we want to do is go after a couple of conserved quantities, and so there's kind of an older nomenclature for that, and so it's so a conserved quantity is what's known as a first integral of the motion. This actually goes way back. This actually goes back to Hamilton and Jacobi and Liouville back in the middle of the 1800s, and so they were thinking in terms of solving differential equations more than they were thinking in terms of dynamics. And so first integrals were ways that you would solve differential equations. All right, so now we have a two-dimensional dynamic. It's a one-body problem, but it's a two-dimensional dynamics. So let's go ahead and write down the Lagrangian. So Lagrangian is going to be 1/2. We have our reduced mass mu, and then I have two coordinates now, and so it's going to be r dot squared, and that's the radial part, and then I'm going to have r squared theta dot squared, and that's the angular part, and then minus u of r. And so the angular momentum, let's go ahead and actually look at dl d theta. Well, dl d theta, there is no explicit theta dependence anywhere, so this is 0. And so it immediately tells me that that d by dt of dl d theta dot is a constant. And so that's going to be a constant of the motion, also known as a first integral. And so what that means is that, or sorry, that's 0. Actually, the thing that's constant is the thing inside, right? So d by dt is actually going to be 0. So d by dt is going to be equal to 0. Okay, so let's go ahead and look at dl d theta dot. So dl d theta dot, that's actually relatively simple because I just actually have the one expression for theta dot there. And so what this is equal to is a mu r squared times theta dot. And so then this is a constant. I'm going to call this p sub theta. We could also, if we want, call that little l. And so little l, or p sub theta, this is the angular momentum of the orbital motion, and it is a conserved quantity. So these are constants. All right, so what we've done is we've actually looked at the Lagrangian, found where dl dq is 0, and then that defines a conserved quantity of the motion. So this is actually a really important relationship here. Okay, and so in fact that deserves a double box. All right, so that is the conserved angular momentum. It is one of the first integrals of the motion. Before I go after another first integral, which will obviously be something like energy conservation, let's look at some consequences of this angular momentum here. And so let's actually think in terms of how the angular momentum relates to aerial velocity. So to do that, let me kind of draw a part of this orbit. I'm going to make this a little bit more general. So let's say I've got the center of mass position, and let's say I've got some kind of an orbit of a mass. And so I've got an orbit, and so here is a position r1. And what that means is it's all just r, but it's r at time 1. So actually, let me do that. R at time 1. And then at some later time, I've got r at time t2. And so that has actually swept out an angle d theta. And what I'm interested in is the area. And so what is the area that's swept out between time t2 and time 1? So let's actually look at the area. We're going to make an approximation, but it's going to be in d theta, and so it'll get successively more accurate as d theta goes to 0. And so essentially what I've got here is a triangle, and so I have an area which is swept out. And it's going to be 1/2 r squared d theta, and so I've got 1/2 base times height of a triangle is its area. The height, we'll call that r, and then the base will be r d theta, so I get the factor of r squared. And this is in a time dt. So let me express this as a dA. All right, so I'm going to have the dA in a time dt is going to be 1/2 r squared d theta dt. Well, that means that's a theta dot. So let me re-express this theta dot in terms of what we've learned before, is that we've got this constant of the motion p theta is equal to mu r squared theta dot. Plug that in, and what I get is a 1/2 r squared, and then p sub theta divided by mu r squared, and then that becomes, and I'm going to actually use the little l because that's kind of the more common way of recognizing that that's angular momentum. So it's going to be L over 2 mu. And so then this is a conserved quantity, right? So you notice that the r's have dropped out. So there's the r squared, there's an r squared, the r squareds have dropped out. The reduced mass is a constant, the angular momentum is a constant, so this is a constant. And so what it means is that there is a dA dt for this orbital motion, which is a constant. And so it says that equal areas are swept out in equal time. So the consequence is that equal areas swept out in equal time. And for those of you who remember your your introductory physics, this is known as Kepler's second law. All right, so the consequence of conserved angular momentum, we can then go into this geometric picture and then show that we have equal areas being swept out in equal time. And that is one of the important Kepler laws. There's actually 3 laws that we'll be talking about, and so we actually did the second law first. So now let's go after conservation of energy. So conservation of energy is actually one of the key principles. So conservation of energy. We already, in some sense, know that this is going to be a conservative problem. The central force, there's no velocity-dependent force, and so there's no dissipation. But let's go back and just remind ourselves that, first of all, there's no explicit time dependence on the Lagrangian. And so the partial of the Lagrangian with respect to time is 0, which means that I can write the total differential of the Lagrangian in terms of a chain rule. And so this will be dl, dqa, and then q dot a plus dl, dq dot a, and then this will be a q double dot a. So what we'll do is use the Euler-Lagrange equations and put in an expression for the dl dq. And so then putting that in there, this tells us that the dl dq is going to be going as q dot a, and then d by dt, coming from the Euler-Lagrange equations, dl dq dot a, and then that's plus dl dq dot a, and then q double dot a. And we can rewrite that. This turns out to be the time derivative of q dot a and dl dq dot a. All right. And so then let me actually rewrite that, bring this over to the other side. And so what I get is that d by dt of this quantity q dot a dl dq dot a minus L is equal to 0. Okay, so that means that this is a constant, right? So this is a constant of the motion, or it's a first integral. And so the first integral is q dot a times dl dq dot a minus L is a constant. So the question is, what is that constant? Well, we can pretty quickly look at this expression here and recognize that that is 2t, and then we're subtracting L from that, and so that's going to be 2t minus t minus u, and lo and behold, that's equal to t plus u, and just for fun, let's just give that the symbol E, and we recognize that that's actually the total energy of the system. And so when there's no explicit time dependence on the Lagrangian, then we get conservation of energy. And so we know that this problem of orbital dynamics now, there is no explicit time dependence, and so we do have an energy conservation principle going. And so that's going to be one of the things that we can use to solve for the dynamics. So then for the orbital dynamic problem, we have that the total energy will be T plus U is equal to E. And so let's go ahead and just write that expression then. So E is going to be 1/2 mu r dot squared plus r squared theta dot squared plus U of r. And let's even rewrite using the theta dot. Let's actually go ahead and use conservation of angular momentum. And what we'll get is that E is equal to 1/2 the reduced mass r dot squared. So there's just the radial kinetic energy we pick up a term which has no velocities in it. And so that's L squared over mu r squared, and then plus u of r. All right? And so what's interesting about this form is that this kinetic energy, which was associated with the theta dot, has now actually turned into an r-dependent term, which can be added to the u of r. And so the u of r was the potential energy of this central force. And so we're going to actually call this V effective. And so V effective now, or let me just rewrite it just one final time, so that the total energy is going to be equal to 1/2 mu r dot squared, and then plus V effective, which is only a function of r, and of the magnitude of r. All right, and so writing that out explicitly, so V effective as a function of r then is equal to 1/2 L squared over mu r squared, and then plus u of r. So let me put that actually into a box, because this is a important consequence of energy conservation and angular momentum conservation. Both have now allowed us to define this effective potential. The effective potentials, we do want to draw that. I mean, we want to make some diagrams on this, because it really helps to understand and to visualize what's happening in terms of these orbital motions let's say explicitly in an inverse square law. All right. So let's actually look at energy as a function of radius. And again, this radius is the relative position between the two bodies. And let's go ahead and now start talking about inverse square law. So the inverse square law has a potential energy, U is equal to minus K over R. The K, that's going to be gravitational constants and masses if it's gravity, but inverse square laws are more general. In fact, we know that the Coulomb law is an inverse square law as well. So let's just call that constant K. And so what that means is that there is a potential energy which is coming down as 1 over r. And so here we have the energy on the vertical axis here. And so here I've got my minus k over r. So the potential energy is getting more and more negative, and it diverges as r goes to 0. But let's look at this other term here. Well, this term, first of all, u of r is negative, and that has to do with the fact that it's an attractive potential. So this new term that came from the conservation of angular momentum, that's like an effective repulsive term. So let's actually draw that. And so that's going to be another dashed line coming up. So this is actually going to be a little bit closer to 0 because it's an r squared, and then it's going to go zooming up as r gets small. And so this curve here is 1/2 mu r squared omega squared. I'm actually writing this in a slightly different form, but you'll actually recognize that this is rewriting the angular momentum in terms of omega. Okay, so that's omega squared. All right, and so what's happening here is that the effective potential is the sum of these two. And so first of all, I've got this negative potential energy from the gravitational attraction, but then I've got this effective repulsive force coming from the conservation of angular momentum. And when I add these two, I get a curve which starts out negative, starts to dip, but then the 1 over r squared actually wins out over the 1 over r, and so then this will actually come up like that. And so what it means is that there's a minimum in the potential, in this effective potential, at some critical, and actually I'll call it really circular, right? That there's going to be a minimum in this effective potential, and that's going to correspond to the circular orbit. And so that is a circular solution to the dynamics. And so that means that r is at a constant value, and that's what makes it a circle. And so that already allows us to solve for circular motion for the circular orbit. And so let's do that next. Oops, don't need that speaker there. All right, so let's actually do that next. So let's look at the circular orbit. And so this is when we're at E min. All right, so it's a circular orbit. Okay, at E min. It's the minimum in the effective potential, and then it's also at this R sub c. So let's actually go ahead and solve for R sub c. And so we want to look at dV effective, dr, and that's going to be 0. And so then that's going to be k over r squared from the gravitational term, and then this will be 2L squared over 2 mu r cubed. And so that's going to be equal to 0. And one thing it allows us to do is to actually get an expression for k. Actually, well, we have the expression for k. That comes from the force. But we get that this is equal to L squared over mu r, actually R sub c. And so then let's solve for that. And so R sub c is equal to L squared over mu k. All right, so let's go ahead and plug in directly some things that we know. So we know that k is equal to the gravitational constant times mass 1 times mass 2. Okay, that's the expression for the circular orbit, right? So we're just plugging that k back in, and we actually have the expression for the circular orbit. So now let's go after more general orbits, and so let me draw this a little bit larger. And so let me actually draw out the energy as a function of radius, and I'll go ahead and do the effective potential. All right, because what I want to do is actually look at the possibility of other types of orbits, right? So we've decided that we've got a circular solution. And so there's a circular solution when I'm at E minimum, and so there's an E minimum coming across here. So E min. And so when the orbit has the minimum possible energy given an angular momentum L, right? So realize that there are actually different curves for different L's. And so L is part of an initial condition. And so what I'm drawing here is, let's say, a single effective potential for a given angular momentum. And so when we're at the total minimum energy, then that is the circular orbit. But I could have energies anywhere above E minimum. And so let's say I have an energy here. All right, let's actually see what that means. Okay, so let's draw this horizontal. Well, what it means is that there are actually two extreme positions on radius. There's an R min, and then there's an R max. Okay. The other thing that you'll notice is that, in a sense, this is kind of looking like a harmonic oscillator, because since this is all just one-dimensional dynamics now, I know it's orbital motion, but for a fixed L, given by the initial conditions of the trajectory, we've got this potential with a minimum. And so you can almost think of this thing as moving back and forth. It's actually oscillating in what almost looks like a quadratic potential here, which would be like a harmonic oscillator, although it's not. That's why the solutions are going to end up being ellipses. But this is going to be moving back and forth between R min and R max. And that is at a, again, this is the total energy. Actually, in this case, you'll notice is negative, right? Because the zero energy is actually there. And so these are known as bound orbits. If my total energy is negative, then I've got a bound orbit, which means that there's going to be an R min and an R max. And that's going to be not, I don't want to say harmonic, but it's going to be a repetitive solution. There's going to be a period for the orbit for a given energy. So let's actually call this E2. Okay. Now just so that we really understand what this graph means, let's actually look at an E3 up here. All right, so what we have up here is, let's say I have a total energy which is positive. And so if my total energy is positive, then it means that there is an R min, but there's no R max. And so this is what's known as an unbounded orbit. And this will turn out to be a hyperbola. It's a hyperbolic orbit. And so this is what you get if something came in from outside the solar system, went whipping around the sun, and then left the solar system, never to return. And so that would be a hyperbolic orbit, and it's an unbound orbit. Now, there's also a energy right at zero. And so if we look at an energy right at zero, then again, there is an R min right there. Again, there's no R max, although it is asymptotic. And so that actually will turn out to be a parabola. And so when I have an orbit whose total energy is zero, then I've actually got a parabolic orbit. Again, you could have something coming in from infinity, whoops around the sun, goes out to infinity, but it starts at infinity with zero kinetic energy. The other thing, really important thing I need to point out is that on this graph is that the difference between any energy that I draw, so an energy I'm just drawing as a horizontal line, but the difference between that energy and the effective potential, this is the radial kinetic energy. That's 1/2 mu r dot squared. And so I've got kinetic energy as the difference between the total energy and the effective potential. So this is the effective potential. And that difference is the radial kinetic energy. So for the unbound orbit, I've got a total energy that's positive with a very high kinetic energy. For the critically bound orbit, which is parabolic, you can see that my kinetic energy actually, which would be this difference out here, that asymptotically goes to zero. And so you can tell then that if you're at this critical orbit that's neither bound nor unbound, that in fact your kinetic energy goes to zero when you go off to r equals infinity. And then if you're a bound orbit, you do have at times, you'll have a radial kinetic energy, but that radial kinetic energy goes to zero at R min and R max. And also R min and R max, because this is now a one-dimensional effective dynamics, those are called turning points. And so there's an inner turning point and an outer turning point. And so the total radial kinetic energy goes to zero at the turning points. Well, I've mentioned that the dynamics become effectively one-dimensional, and so we had, with the effective potential depending on R, with the additional kinetic energy term, which came from conserved angular momentum, that gets added to the potential energy to become part of the effective potential. And so then everything is just R, and so we've got an expression for R dot, and then we've got an effective potential, which also goes as R. But it doesn't mean that theta has disappeared. I mean, this is still, the orbit is still a two-dimensional orbit in the plane. And so we do want to get back to theta to figure out how theta and r are linked in these orbits. And so that's going to ultimately lead us to these conic sections. So let's look at, we'll start again with kinetic energy. Total energy. And so it's going to be total energy is equal to 1/2 mu r dot squared. I am going to go ahead and put in the 1/2 L squared over mu r squared, and then a plus u of r. So there's our total energy. So we've got our potential energy term, our radial kinetic energy term, and then we've got the angular orbital contribution to the kinetic energy. So what I'm going to do is I'm going to actually solve this. So E is a constant. E is a given an initial condition for an orbit, right? So E is an initial condition and L is an initial condition. So E and L are constants of a given orbit. Now, different orbits will have different E's and different L's, but for a given orbit, E and L are constants. And so what I'm going to do is solve this equation for r dot, and so that's actually a fairly simple expression. So r dot turns out to be equal to plus or minus the square root of 2 over mu, and then I have E minus u, and then this will be minus L squared over mu squared r squared. Okay. Well, that still isn't where I want to get to. I'm really looking for some expression of theta as some function of r. So let me actually use a simple chain rule to produce an identity. So d theta is going to be d theta dt, and then I can have dt dr, and then I can have dr. Right? So that's just simple chain rule. That allows me to write this thing as a theta dot over an r dot times dr. And the reason why I wanted to put it into theta dot is because I always have that expression for the angular momentum in terms of theta dot, and so then I can write this thing as an L over a mu r squared r dot dr. Okay? And so what that allows me to do is then integrate both sides. And so I've got a d theta on one side, I've got a dr on the other side. Let me go ahead and throw an integral up here. And so what I get is, and then this r dot is coming from over here, right? So r dot, oops, it's right there, all right? Go ahead and integrate the left-hand side, so that gives me a theta of r. And then on the right-hand side, I still have an integral. I don't get rid of the integral, but I now have an explicit expression. It's going to be plus or minus L over r squared dr divided by the square root of 2 mu, and then e minus u minus L squared over 2 mu r squared. And then that's going to then be integrated between limits. Now what I'll do is I'll actually establish that I want theta to be 0 when I'm at the minimum. And so to do that, I'm actually going to go ahead and put a pi over 2 over here. I'm just adding a relative angle to the solution. But then this allows me, I'm going to put a box around this, because this now, if I can do that integral, gives me theta as a function of r, and that is the trajectory, right? So that actually maps out the trajectory. Given whatever the E and the L are for this orbit, I then can define the trajectory in the plane, and it would be defined in terms of theta as a function of r, or you could flip that and call it r as a function of theta. So let's go ahead and solve this. And so what we want to do is do a substitution of variable, where what we're going to use is the fact that we've got a 1 over r dependence, which is showing up in several different places in that integral. So let's go ahead and make the substitution that u is equal to 1 over r. And so then I can write theta as a function of u. And so then that'll be, I'm going to pull out the angular momentum, got the integral of du, and then over square root of 2 mu e plus 2 mu ku minus L squared u squared, and then plus pi over 2. Let's rewrite that. In fact, actually, well, we actually can recognize that. In fact, let me just draw it like this. I mean, so we've actually got that over the square root of au squared plus bu plus c. Now that actually turns out to be something you can look up pretty easily in an integral table. So that's going to be L, and so I'm just actually going to plug some things in here with some minus signs. It's going to be minus 1 over the square root of minus a. A is going to turn out to be negative, so it's fine. The arc sine of 2au plus b divided by square root of b squared minus 4ac, and then plus pi over 2. All right. Let me put this back into, so we've actually done the integral now, so let me actually put this back into r. So it's going to be theta of r is equal to pi over 2 minus the arc sine of, kind of an ugly argument here, so it's going to be L squared over mu k times 1 over r minus 1 and over square root of 1 plus 2e L squared over mu k squared. That's pretty ugly. Let's continue to find ways of simplifying that. So that's going to be, let's have alpha be L squared over mu k. And let me try an epsilon, which is going to be a square root of 1 plus 2e L squared over mu k squared. All right. Now with those, I actually get a really nice parameterization then. So if I use alpha and epsilon in this expression for theta, then I'm going to go ahead and take a cosine. But what I get is an expression that looks like this. I get alpha over r is equal to 1 plus epsilon cosine theta. So in the end, we've got a pretty simple expression here. And for those of you who are good at geometry, you may actually recognize that this is a conic section. So this is a good point to do a review of conic sections. So first of all, let's look at an ellipse. And let's go ahead and draw this out so we can remind ourselves about the various ways of parameterizing or describing an ellipse. All right, so I've got a focal point at one end, a focal point at the other end. I've got a center, and so there's a distance from the center to a focal point. I've got B is a semi-minor axis, and then A is a semi-major axis. And then at one of the focal points, let's say this is one of the focal points, I can look at this lateral distance here. I'm going to go ahead and call this alpha. And then I'm also going to define epsilon, which is known as the eccentricity. So that's going to be this distance c, which is the distance between the center to one of the focal points, divided by the semi-major axis. And now for an ellipse, it's actually defined that the eccentricity is less than 1. So it turns out that this ellipse can be parameterized or described as a function of r, and so, or r is a function of theta, and so this turns out to be equal to a 1 minus epsilon squared divided by 1 minus epsilon cosine theta. And if we bring in the definition for alpha, this turns out to be alpha over 1 minus epsilon cosine theta. And that actually makes connection back with the conic section that we looked at last time. If you just go back, actually, let me just go ahead and do that. So if we go back here, we saw that we have alpha over r equal to 1 plus epsilon plus cosine theta. And that's showing up right there. And we get the same thing here. So alpha over r, bring the r down over here, and then I have a, in this case I have a minus epsilon. That's actually okay. I can have a alpha over r 1 minus cosine theta. Actually, I'm just flipping the, in this case actually I flipped by pi the definition of cosine theta. Okay. Now it turns out that we can also write this thing in terms of, or we can actually describe an r min. And so that's going to be the minimum distance between a focal point and the point of closest approach. And so that is a 1 minus epsilon, which is also alpha over 1 plus epsilon. And then there's an r max, which is equal to a 1 plus epsilon is equal to alpha over 1 minus epsilon. R min is, actually, let's see, R min I think is called the perigee. And then R max, the maximum distance, is the apogee. I think I have that definition right. All right, and so then we can see that the equation that we got when we were solving for the inverse square law is, in fact, a conic section. And I've already down here made connections with the parameters that we defined when we were doing the integral. We defined an alpha and an epsilon. And so here, if we bring this 1 minus epsilon down to the other side, it's this term here, bring it down over here, then I get this expression. And we can plug in and I get k over twice the energy. There's a similar expression for B in terms of alpha and epsilon. These are things that you can look up in tables. They would certainly, if they're needed on the next midterm, they'd be given on the equation sheet. But then B, the semi-minor axis, is given by the angular momentum divided by the square root of 2 mu times the total energy. And I just want to point out that we've proven now Kepler's first law. So Kepler's first law, that the orbits in an inverse square potential or force, inverse square force, the orbits are conic sections with the center at one of the one focus of the conic section. So Kepler's first law is just basically that the orbit is a conic section. Okay, so we've now demonstrated Kepler's first law, that the orbits, gravitational orbits, are a conic section. If you remember, Kepler's second law was about equal areas and equal time. Here we are. Kepler's second law was equal areas and equal time. So now let's go after Kepler's third law. And so they get a little bit more quantitative as they move up, right? So the first law is just descriptive. It says they're conic sections. Second law says that equal areas and equal time. Third law gets more specific in terms of how the period depends on the semi-major axis. And so let's go after that. So, let's look at Kepler's third law. So Kepler's third law. All right. So what I'm going to do is let me start out with equal area and equal time. So Kepler's second law, so dA dt, is equal to L over 2 mu. And I can rewrite that as a dt is equal to 2 mu over L times dA. All right. Let me go ahead and integrate that. I know that it looks like we're not really doing a lot here, but I can just integrate that. So the period is the integral over the period of dt, and then that is equal to 2 mu over L times the integral over the area of the ellipse times dA. Well, that actually turns out to be easy because t is then equal to 2 mu over L. The area of a ellipse is just pi AB. Okay, so that's great. We actually have an expression for the period as a function of the product of the semi-major and semi-minor axis. Let's go ahead and plug in our expressions that we had on the last page. So that's going to be 2 mu over L, pi. Alpha was k over twice the energy, and then B was L divided by square root of 2 mu, and then the absolute value of the energy. All right, so I can actually then combine some terms there. I get that the period of the orbit is equal to pi k square root of mu over 2, and then I have 1 over e to the 3/2. All right. That's a little bit ugly, so let me square both sides, and what I get is that t squared is equal to pi squared k squared mu over 2, and then 1 over e cubed. All right. This is actually one way of expressing Kepler's third law. That's not the way that he expressed it. He went on to actually make the connection between energy and the semi-major axis, and that's actually given by 1 over e cubed is equal to 8a cubed over k cubed. Plug that back in, and what we finally get is the normal way of expressing Kepler's third law is that t squared is equal to 4 pi squared k, oops, that's a mu, 4 pi squared mu over k, and then a cubed. And so that deserves a double box. So Kepler's third law says that there's a proportionality between the square of the period and the cube of the radius. It's often called the radius, but this would be the semi-minor axis of an elliptical orbit. And so we've been able to go through and derive all of Kepler's third laws. First one was that they're conic sections. Second is that equal area and equal time. That actually came straight out of conservation of angular momentum. And then the third, Kepler's third law, is the most quantitative, saying that there's a relationship between the square of the period and the cube of the radius.